Hello and welcome. In this video, we're going to be taking a look at the basic concept of sequences and series, and more specifically, infinite sequences and series. Now, there's going to be a fair number of definitions in this video, so let's get started. A sequence, first of all, is just a list of numbers, and a list is different from a set in the fact that a list has an order. Now, we have this notation. We can say that A sub n is just some sort of number with an index of n, and we would start with n equal to 1, and we can continue going on forever. So the first number, or the first item in this sequence is a1, second item is a2, third item is a3, and so on. In general, we would have the nth item, and then we would continue on forever. If this is an infinite sequence, it has no end. Now, oftentimes there's going to be some kind of pattern to these numbers, and an is going to be some explicit formula that gives us the nth number in the sequence. Here's an example. If we were to say that an is just n, then the nth number in our sequence is n itself. That means that the first number in our sequence is 1, the second number in our sequence is 2, the third number in our sequence is 3, and of course you can see this pattern. This is simply all of the positive integers. We can start getting a little more interesting if we have 2n from n equals 1 to infinity. Now our first term, when n equals 1, will be 2 times 1, which equals 2, and our second term, when n equals 2, will be 2 times 2, which is 4. Third term will be 6, and you can see that this generates all of the even integers. We could do something kind of similar, actually, to get a sequence of all of the odd numbers. If we wanted to get the positive odd number starting at 1, then we could simply subtract 1 from all of these numbers. So the sequence of odd numbers could be 2n minus 1. Now, it's quite possible that we may have a sequence of numbers given to us and need to come up with the explicit formula for it. For example, 2, 5, 8, 11, 14. Well, there's a nice pattern that you might be able to see, and that is that every next number in the sequence is simply 3 more than the previous number. To come up with a formula for this, we could say, well, a1 is equal to 2, a2 is equal to 5. But that's not super useful on its own, so maybe instead of writing 5, we might want to write 2 plus 3. And a3 is 3 more than that. Well, that's 2 plus 3 plus 3. And a4 is equal to 2 plus 3 plus 3 plus 3. And now you see that the pattern is all there. But we can condense this notation. Well, if I'm adding 3 times, that's the same thing as 2 plus 3 times 3. If I'm adding 3 twice, that's just 2 plus 2 times 3. And finishing off all of that more compact notation, we can see a much easier pattern. Instead of 2, 5, 8, 11, 14, we can see this nice pattern, 0, 1, 2, 3. Well, those numbers are exactly 1 less than the index. When n equals 1, we have 0 times 3. When n equals 2, we have 1 times 3. Well, then that means that the nth number in the sequence, we should just be able to write 2 plus n minus 1 times 3. And that's how we would be able to turn this sequence of numbers into a nice compact formula. This sequence is 2 plus 3 times n minus 1 from n equals 1 to infinity. We could even tidy that up a little bit more. That would be simply 3n minus 1. And once we've come up with a nice compact notation to get the nth number in a sequence, you can always check your answer by letting n equal 1. 3 times 1 minus 1 is 2, so that's good. When n equals 2, 3 times 2 minus 1 is 5. That seems to work there. 3 times 3 minus 1 is 8. And sure enough, we can seem to get it to match along with our first few numbers in the sequence. But now, with this handy formula, we can also jump to the 152nd number in the sequence if we want to, just by plugging 152 in for n. Now, it's worth noting that not every sequence necessarily has a convenient formula like that. In fact, sometimes the easiest definition for a sequence is actually a little bit more intricate. And we could take a look at the Fibonacci sequence as a clever example. The Fibonacci sequence is an example of a sequence that is defined recursively. Rather than using an, why don't we use fn, f for Fibonacci? Well, f1, the first Fibonacci number, is 1. And f2, the second number in the Fibonacci sequence, is also 1. But the nth number in the Fibonacci sequence for n greater than or equal to 3 is actually the sum of the two immediately preceding Fibonacci numbers. So what this does is it establishes the first couple Fibonacci numbers, 1, 1. But after that, we have to calculate each new number using the two previously defined Fibonacci numbers. 1 plus 1 will give us 2 as the third Fibonacci number. 1 plus 2 gives us 3 as the fourth Fibonacci number. 2 plus 3 is equal to 5, which is the fifth Fibonacci number, and the only Fibonacci number where the nth number equals itself. And then we are up to 8 for the sixth Fibonacci number. And this continues onward and onward. Now, there are so many fun facts about the Fibonacci sequence that could be a whole separate video. There's a lot of interesting properties about what is happening in the ratio of two adjacent numbers. There are fun facts about where we find Fibonacci numbers occurring in nature and science, but like I say, that could probably be saved for a future video. We're going to be largely concerned with sequences for our next couple topics in series is looking at the limit of a sequence and seeing whether or not it converges. Now, the definition for the limit of a sequence is very similar to the limit of a function. We can get a little lazy with our notation sometimes, and instead of saying infinite sequences have to always be written as the curly brackets around an from n equals 1 to infinity, we can assume that when we put an in curly brackets, we already mean a sequence. And since we're really referring to infinite sequences here, we're going to be taking the limit as n goes to infinity. We say that the limit as n goes to infinity of an is equal to L to mean that we can make each term or each item in that sequence get closer and closer to L. We can make it as close to L as we like by taking n to be a sufficiently large index. Now, if that limit exists, then we say that the sequence is convergent or that the sequence converges. Otherwise, if the limit doesn't exist, then the sequence diverges or the sequence is divergent. That doesn't necessarily mean that the limit equals infinity, and that means it doesn't exist. It's quite possible that we may just have that these terms don't follow any kind of pattern that gets closer and closer to a single integer. We may just have that the sequence of numbers doesn't seem to ever get closer to one specific number. Let's take a look at a couple examples. Let's start with the sequence 1 over n plus 1. So when n equals 1, we have a half, and when n equals 2, we have 1/3. When n equals 3, we have 1/4, 1/5, 1/6, 1/7, and so on. You can imagine what these are going to be getting closer to. These fractions keep decreasing, and we get closer and closer to 0. And by taking a look at the limit, as n goes to infinity of this expression, 1 over n plus 1, well, we can check and make sure that that does in fact equal 0. We could always divide numerator and denominator by n. And we see that the numerator, 1 over n, goes to 0, and the denominator, 1 plus 1 over n, goes to 1. That gives us 0. So this sequence converges to the limit 0. In this example, 1 over 2 to the n from n equals 1 to infinity, well, when n equals 1, we end up with 1/2. But when n equals 2, we end up with 1/4. When n equals 3, 1/8, 1/16, 1/32, and etc. And you can see that this is also getting smaller and smaller, although it's getting smaller a lot quicker than the previous sequence. And that's going to make quite a big difference when we start thinking about what happens in series where we add these together. But first and foremost, we can double check that this is a convergent sequence. If we take the limit as n goes to infinity of 1 over 2 to the n, well, this is the same thing as 1/2 to the power n. And since 1/2 is a number between 0 and 1, as we start to increase the exponent n as n goes to infinity, we will approach 0. So those are both convergent sequences. But like I say, this is getting ahead here, but if you start adding them together, they may have different results. Let's take a look at a sequence that is divergent. Here is the sequence -1 to the power of n minus 1. So if we're starting at n equals 1, that gives us an exponent of 0, and -1 to the 0 is just like anything else to the power of 0. It equals 1. And if we plug in n equals 2, we get -1 to the power of 1. And just like anything to the power of 1, it's itself. So we end up with -1. Now, when we plug in n equals 3, 3 minus 1, well, essentially it gives us an even power. And -1 to any even power is 1. -1 to any odd power is -1. So when we plug in n equals 4, we're going to get -1 cubed. So that's an odd power. And you can see that this just alternates back and forth. Now, when we start taking a look at the limit of that sequence, we're taking a look at a sequence of -1, +1, -1, +1. And at no point in time are those two alternating numbers going to get closer to the same value. There's no number that we can make the terms an get as close to as we like by taking n sufficiently large. So this is divergent. Now, as you can probably imagine, since determining whether a sequence is convergent or divergent depends on limits, then we can really start applying a lot of the limit laws and say, well, if we have two convergent sequences and we were to make a new sequence, which is just the sum of those two terms, then the new resulting sequence should also be convergent. And we can just sum up a few of those properties here quickly and move on to series. Applying the limit laws to sequences, if we start off with convergent sequences an and bn, and where we have c just being some kind of constant, then the following are also convergent. A constant multiple of a convergent sequence is also convergent. The sum or difference of convergent sequences is still convergent. A product of convergent sequences is convergent. A quotient of convergent sequences is convergent as long as the denominator does not have a limit equal to 0. And even a power of a convergent sequence is still convergent so long as we have a positive power and each term an is also positive. And by properties of continuous functions, we can even extend this a little bit. If we start off with a function that is continuous at L and a convergent sequence an whose limit equals L, then the sequence f of an is convergent and it has a limit equal to fl. Now, with a few of these basic facts on sequences under our belt, let's take a look at series, which is nothing more than really just the sum of a sequence. Now, we've seen series before in a previous video when we took a look at trying to calculate the definite integral of a function using Riemann sums. So a series here is really just the sum now of the terms of any sequence. A sequence would be in order. An would be each term in that sequence, and we write sigma to mean that we want to sum up each of those individual terms. So if we start at n equals 1 and go to infinity, this is an infinite series, and we add a1 plus a2 plus a3 plus a4 and continue onward. The nth term in that series would be an, and then we would continue onward and onward. Now, when we talk about the sum of infinitely many numbers, sometimes we have to wonder if that even makes sense. Can that possibly equal some value? It doesn't always make sense. For instance, taking a look at that first sequence, 1, 2, 3, 4, 5, which is just the sequence n, what if we were to add all those numbers together? The series, 1 plus 2 plus 3 plus 4 plus 5 plus so on, doesn't make any sense. Because if we start adding terms, then the sums get increasingly large, and it would never equal some value. But we might be able to find some kind of series where the numbers themselves get small enough that when we add cumulative numbers, it might actually get us some value. We saw this sequence before, 1/2, 1/4, 1/8, 1/16, 1/32. What if we start turning that into a series and start adding 1/2 plus 1/4 plus 1/8 and so on? Well, this is actually a pretty famous problem called Zeno's paradox. And really, he was observing that if you want to get across the room, you have to walk half the way across the room. Well, from there, you would still have to get to the wall on the opposite side of the room, and you would have to walk a further half that distance, which would be 1/4. You'd have to walk a further 1/2 of the remaining distance, which is 1/8. But if you continue this, 1/2 plus 1/4 plus 1/8 plus 1/16, will this fraction ever get you equal to 1 the entire way across the room? In order to make sense of this, what we need to do is calculate something called a partial sum. An nth partial sum is just the sum of the first n terms in a series. So the third partial sum is just adding up the first 3 terms in a series, and the 100th partial sum is adding up the first 100 numbers. In other words, if you're given a series, which is sigma notation here, the sum from n equals 1 to infinity of an, which is a1 plus a2 plus a3 and so on, the nth partial sum, let's say, is Sn, and Sn will, again, be in sigma notation, but not going to infinity. We're going to stop when we get to an index n. Well, that means that we shouldn't be using n as the label on each of our terms. We should probably use an index such as I, and I can start from 1. That would give us a1, and go upward a2, a3, a4 until I reaches the value of n. And that is what we call the nth partial sum. Now, let's see what the nth partial sum looks like for this particular series from Zeno's paradox: 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32. If you recall, 1/2, 1/4, 1/8, 1/16, and 1/32, and so on, was one of our sequences from earlier in this video. That was simply 1 over 2 to the n. Now, what about those partial sums? S1 would be just the sum of the first term. Of course, that just equals the first term itself, since we're not even really adding 2 terms together. But taking a look at the second partial sum, well, that would be 1/2 plus 1/4, which is 3/2. The third partial sum is 1/2 plus 1/4 plus 1/8. Well, that is equal to 3/4 plus 1/8, which is 7/8. And the fourth partial sum would be 1/2 plus 1/4 plus 1/8 plus 1/16, which is nothing more than 7/8 plus 1/16. And that is equal to 15/16. And at this point in time, you may have noticed that the partial sums actually form a sequence: 1/2, 3/4, 7/8, 15/16, and so on. Let's see if we can come up with a formula for the nth partial sum. Sometimes it's a little easier to see, well, 1/2, 3/4, 7/8, and 15/16 are all getting pretty close to just being equal to 1. The higher we go through the partial sums, the closer this fraction ends up becoming to 1. So let's take a look at that. 1/2 is 1 minus a half. It's not that close. But 3/4 is even closer to 1. It's 1 minus 1/4. 7/8, well, it's 8/8, which is 1 minus 1/8. And 15/16 is actually just 16 over 16, which is 1 minus 1/16. And these numbers, 1/2, 1/4, 1/8, and 1/16, well, that's something we've seen before. So actually, you might be able to recognize the pattern here and say that the nth partial sum is just 1 minus 1 over 2 to the n. 1/2, 1/4, 1/8, and 1/16, respectively, is what we're missing from 1. It's what we're subtracting from 1 for the nth partial sum. With this partial sums now forming a sequence, we can take a look as n goes to infinity. The limit, as n goes to infinity, of the partial sum, 1 minus 1 over 2 to the n, can be calculated by a few limit laws here. Since 1 is just a constant, and we can rewrite 1 over 2 to the n as 1/2 to the n, we can see that this 1/2 to the n is going to be getting smaller, and this limit is equal to 1. So we say that the sequence of partial sums is convergent. But more than that, now we can actually say that this series is convergent. And that's how we define a convergent series. For any given infinite series, where we could write the sum from n equals 1 to infinity of an, if the sequence of partial sums, that would be the sequence Sn, if it's convergent and the limit of that sequence equals s as some sort of real number, then we would say that the series is convergent, and we write that the sum of that series equals s. But if the sequence of partial sums is divergent, and the sequence either has a limit going to infinity, negative infinity, or just simply does not exist, then the series is divergent. Let's take a look at one of those other classic sequences and take a look at its series. Earlier we saw the sequence -1 to the power n minus 1 from n equals 1 to infinity. And that was just an alternating sequence, 1, -1, 1, -1, and so on. Its series would be adding all those terms together. Changing the notation here to sigma notation from n equals 1 to infinity, we have 1 minus 1 plus 1 minus 1 plus 1, and so on. And this is a very confusing series because it really depends on how you would think about adding two consecutive terms. We know that addition is associative, so it doesn't really matter which of these terms we add together. We could add all of the ones together and all of the negative ones together, but then that would be infinitely many ones and infinitely many negative ones, and we wouldn't really be able to define that. But if we were to add two consecutive terms, 1 minus 1, that would be 0. 1 minus 1, that would be 0. 1 minus 1, that would be 0. And adding the results of those would be just adding an infinite series of 0. Well, that would equal 0. But if we were to add the next adjacent terms, -1 plus 1 and -1 plus 1, well, we end up with a bunch of zeros. We haven't added the original 1 together. So maybe the series equals 1. The only way to determine whether this is truly convergent or divergent is by looking at the definition. Does this limit exist? Let's take a look at the first 4 or 5 partial sums. The sequence of partial sums would start off with the first partial sum, which is simply just 1. The second partial sum would be the sum of the first two terms, 1 minus 1, which is 0. The third partial sum, 1 minus 1 plus 1, which is 1. And the fourth partial sum, 1 minus 1 plus 1 minus 1 is 0. And so this sequence will continue to flip back and forth, 1, 0, 1, 0, 1, 0, forever. If we take the limit of this particular sequence, then we'll see that we can never make this sequence get closer and closer, or as close as we desire, to some real number by taking n sufficiently large. We cannot let this sequence get as close to 1 as we like, since it's always going to flip back to 0 on the next term. And we can't let it get as close to 0 as we like, because it always flips to 1 on the next term. Now, there are plenty of convincing arguments that perhaps the series here that we're talking about equals 1/2. And now they're very convincing arguments, and actually a lot of the mathematics and scientific community may even agree that this is 1/2. However, the limit of these partial sums is not something we can contest. 1, 0, 1, 0, 1, 0 doesn't ever approach one single value. So we'd have to say that the limit does not exist. And by definition, since the limit of this particular sequence does not exist, we will have to say that the series is divergent. All right, well, we've seen a few examples of sequences in series, and some are convergent and some are divergent. It's not always easy to tell which is which, though, and especially that is true for series. Finding the limit of a sequence isn't terrible. Finding out the limit of partial sums can be a little bit trickier. And we've seen a couple examples like 1/2 plus 1/4 plus 1/8 plus 1/16. Well, yes, that's convergent. And that is actually one example of a very special kind of series that we'll see in a future video. And that makes it very easy to classify them as convergent or divergent. But in many other circumstances, such as 1/2 plus 1/3 plus 1/4 plus 1/5, it's a convergent sequence, but are the partial sums convergent? We'll take a look at that and many other ways to tell if a series is convergent or divergent in future videos. So thanks for watching, and I'll see you in the next video.